Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we understood that what is Laplace transform and why it is used in the circuit analysis. So in this video, let us see the Laplace transform of some basic functions which we will frequently encounter during our circuit analysis. So like I said in the previous video, here we will assume that all the functions exist only for the t greater than or equal to 0. Or in other words, all the functions are the causal. Because almost all the signals which we will encounter during our circuit analysis only exist for the t greater than or equal to 0. So that is why here we will use only the one-sided Laplace transform. So first, let us start with the impulse function and let us see the Laplace transform of this impulse function. But before we find the Laplace transform, first we should be aware about what is the impulse function. So this impulse function is a very short duration pulse with a very high amplitude. And graphically, this is how it can be represented. So like I said, the impulse function is a very short duration pulse. Let's say it exists from the minus epsilon to plus epsilon and its height is equal to 1 divided by epsilon. Now as this epsilon tends to 0, then this pulse width will get narrower and at the same time the pulse height will also increase. That means the impulse function or the delta function is a very high amplitude pulse with the very short duration. And that is why typically it is represented by the arrow at the origin. And this function is generally represented using the symbol delta t. So typically during the circuit analysis, we might encounter a very short duration pulse with the very large voltage or the current. And during the circuit analysis, that type of signal can be modeled as an impulse function. So mathematically if we see, then this impulse function is 0 everywhere except that t is equal to 0. But at t is equal to 0, its amplitude will be very high. So if we integrate this impulse function, then the integration will be equal to 1. So here we are assuming that this a is less than 0 and this b is greater than 0. That means this integration is carried out around the origin. Or further, we can extend these limits from 0 minus to infinite, where this 0 minus indicates that it is the time just before the t is equal to 0. Now another important property of this impulse function is that when we multiply this impulse function with some random function phi of t, then we will get the delta t times phi of 0, where the phi of 0 is the value of the function at time t is equal to 0. So if we integrate this delta t times phi of t over some integration limit a to b, then we will get this delta t times phi of 0. So as you know, this phi of 0 is the constant and therefore we can take it outside. And as we have seen, this integration a to b, this delta t times dt is equal to 1. That means eventually we will get phi of 0. That means if we multiply the delta t with the phi of t and if we integrate this term over some integration limit a to b, then we will get the value of the function at time t is equal to 0. And of course over here we are assuming that this a is less than 0 and the b is greater than 0. So instead of a and b, we can extend the integration limits from 0 minus to infinity. That means if we multiply any function with the delta function and if we integrate it from 0 minus to infinity, then we will get the value of the function at time t is equal to 0. So using this property of the impulse function, let us find the Laplace transform of this delta function. So as per the definition of the Laplace transform of this delta function is equal to integration 0 minus to infinity delta t times e to the power minus st times dt. Now as we have seen earlier, when the impulse function gets multiplied with any other function, then it gives the value of the function at time t is equal to 0. So here it will give the value of the e to the power minus st at time t is equal to 0. So as you know, this e to the power minus 0 is equal to 1. And therefore, we will have integration 0 minus to infinity delta t times dt. And as you know, that is equal to 1. So we can say that the Laplace transform of this impulse function is equal to 1. So similarly, now let us find the Laplace transform of the unit step function. So this unit step function is usually represented using the symbol u of t. So the value of this function is 1 for the t greater than or equal to 0 and this function is 0 for t less than 0. So in the circuit analysis, when we close the switch, then suddenly the voltage will appear across the circuit. And that voltage across the circuit can be represented using this unit step function. So now, let us find the Laplace transform of this unit step function. So the Laplace transform of this unit step function is equal to integration 0 minus to infinity u of t times e to the power minus st times dt. So during this limit, the value of this function is equal to 1. So we can say that is equal to integration 0 minus to infinity 1 dot e to the power minus st times dt. Now as you know, the integration of the e to the power minus st is equal to e to the power minus st divided by minus s. And here, the integration limits will be from 0 to infinity. So after putting the limit, we can write this expression as minus 1 divided by s times e to the power minus infinity minus e to the power 0. So as you know, this e to the power minus infinity is equal to 0, while the e to the power 0 is equal to 1. That means this expression will become minus 1 divided by s times 0 minus 1, or that is equal to 1 divided by s. That means the Laplace transform of this unit step function is equal to 1 divided by s. Now in the previous video we have seen that for the every function which is a Laplace transformable, the region of convergence is also defined, and this ROC defines the range over which the Laplace transform exists. So we have seen that this is the condition for the existence of the Laplace transform. So for the given function, the integration converges when the real part of the s or the sigma is greater than 0. That means for the unit step function, the region of convergence is sigma greater than 0. So similarly, let us see the Laplace transform of the time shifted unit step function. So this u of t minus t is the time shifted unit step function. That means instead of the time t is equal to 0, this function will start at the time t is equal to capital T. And before that, the value of this function is equal to 0. So the Laplace transform of this function can be given as 0 minus to infinity u of t minus t e to the power minus st times dt. Now this function is 0 when the t is less than t, and beyond that this function is equal to 1. So we can write this integration as integration t to infinity 1 dot e to the power minus st times dt. And once again, the integration of the e to the power minus st is equal to e to the power minus st divided by minus s. And here, the integration limits will be from t to infinity. So once again, if we put these limits, then we can write this expression as minus 1 divided by s times e to the power minus infinity minus e to the power minus st. Now as you know, this e to the power minus infinity is equal to 0. So further we can write this expression as minus 1 divided by s 0 minus e to the power minus st, or that is equal to e to the power minus st divided by s. So we can say that the Laplace transform of this time shifted unit step function is equal to e to the power minus st divided by s. And once again over here, the region of convergence is sigma greater than 0. That means for this Laplace transform to exist, the real part of the s or the value of the sigma should be greater than 0. So in this way, we have seen the Laplace transform of the impulse as well as the unit step function. So similarly, now let us see the Laplace transform of the ramp function. So this ramp function is usually denoted as the r of t, and mathematically it can be represented as t times u of t, where this u of t indicates that this function exists only for the t greater than or equal to 0, and for the t less than 0, the value of the function is equal to 0. So the Laplace transform of this function can be given as integration 0 minus to infinity t times e to the power minus st times dt, because here this u of t just indicates that this function exists for the t greater than or equal to 0. So now, by using the integrating by parts, we will find the integration of this term. So as per the formula, this integration u of dv can be given as u times v minus integration of v times du. So using this formula, we will find the integration of this term. So here, let's say this u is equal to t and this dv is equal to e to the power minus st. That means this u is equal to t and this dv is equal to e to the power minus st. So as per this formula, the first term is u times v, where the v is the integration of this e to the power minus st. And as you know, the integration of the e to the power minus st is equal to e to the power minus st divided by minus s. That means here, the first term will be equal to t times e to the power minus st divided by minus s. And here, the integration limits will be from 0 to infinity. So in this term, if we put the limit as infinite, then this e to the power minus infinite will become 0. And the second time, when we put the limit as t, then this t will become 0. That means for both the limits, the value of this term will become 0. Similarly, if you see the second term, then that is equal to integration v times du. So once again over here, this v is the integration of this term, and that is equal to e to the power minus st divided by minus s. And this du is the differentiation of this first term. So as you know, the differentiation of the t is equal to 1. Therefore over here, we will have this 1 dot e to the power minus st divided by minus s. So here, this minus minus will get cancelled out. So over here, we will have integration 0 minus to infinity e to the power minus st divided by s times dt. So once again, if we integrate this term, then we will have e to the power minus st divided by minus s square. And here, the integration limits will be from 0 to infinity. So in this expression, if we put the limit as infinity, then this e to the power minus infinity will become 0. And for the second limit, this e to the power 0 is equal to 1. So here, the first term will become 0, while for the second term, we will have 1 divided by s square. So we can say that the Laplace transform of this t times u of t, or the Laplace transform of this ramp function, is equal to 1 divided by s square. And once again, this function is a Laplace transformable when the sigma is greater than 0, or in other words, when the real part of the s is greater than 0, because then and then only this integration will converge. So that is the Laplace transform of the ramp function. So similarly, let us see the Laplace transform of the parabolic function, that is equal to t square times u of t, where here this u of t indicates that this function exists only for the t greater than or equal to 0. So as per the definition of the Laplace transform, the Laplace transform of this function is equal to integration of 0 minus to infinity t square times e to the power minus st times dt. So once again, using the integrating by parts, we will find the integration of these terms. So as you know the formula of integrating by parts, the integration of this u times dv can be given as u times v minus integration of v times du. So in this case, let's say the u is equal to t square and this dv is equal to e to the power minus st. That means here, this v is the integration of this term, that is equal to e to the power minus st divided by minus s. So as per this formula, our first term will be equal to t square times e to the power minus st divided by minus s. And here, the integration limits will be from 0 to infinity. So when we put the limit as infinity, then this e to the power minus st will become e to the power minus infinite, and that is equal to 0. And for the second time, when we put the limit as 0, then this t square will become 0. That means for both the limits, the value of this term is equal to 0. So similarly, if we see the second term, then that is equal to integration v times du. So in this case, the differentiation of this term is equal to 2t. That means here, our second term is equal to integration 0 minus to infinity is 2t times e to the power minus st divided by minus s times dt. So once again over here, this minus minus will get cancelled out. And we will have this 2 divided by s integration 0 minus to infinity t times e to the power minus st times dt. So we have just seen that the integration of this term is equal to 1 divided by s. That means we will have this 2 divided by s times 1 divided by s square, or that is equal to 2 divided by s cube. That means the Laplace transform of this t square times u of t is equal to 2 divided by s cube. And once again for this function, the ROC is equal to sigma greater than 0. That means this integration converges when the real part of the s or the sigma is greater than 0. So here we have seen that the Laplace transform of the ramp function or this t times u of t is equal to 1 divided by s square, while the Laplace transform of the function t square times u of t is equal to 2 divided by s cube. So in general we can say that the Laplace transform of the function t to the power n times u of t is equal to n factorial divided by this s to the power n plus 1. So similarly, now let us find the Laplace transform of the exponential functions. So now we will see the Laplace transform of this function e to the power minus at. And here this u of t along with this exponential indicates that this function exists only for the t greater than or equal to 0. So the Laplace transform of this function can be given as integration 0 minus to infinity e to the power minus st times e to the power minus st times dt. So that is equal to integration 0 minus to infinity e to the power minus s plus a times t times dt. So as you know, the integration of this term is equal to e to the power minus s plus a times t, and in the denominator we will have minus s plus a. So here the integration limits are from 0 to infinity. So if we put the integration limits, then we will have minus 1 divided by s plus a times e to the power minus infinity minus e to the power 0. So as you know, the e to the power minus infinity is 0, while the e to the power 0 is 1. So eventually we will have 1 divided by s plus a. That means the Laplace transform of this e to the power minus at times u of t is equal to 1 divided by s plus a. So for this function, integration converges when the real part of the s or the value of the sigma is greater than minus a. So this is the ROC for the given function. So similarly, now let us see the Laplace transform of the function e to the power at. So once again, the Laplace transform of this function can be given as 0 minus to infinity e to the power at times e to the power minus st times dt, and that is equal to 0 minus to infinity e to the power minus s minus a times t times dt. So we have seen that the integration 0 to infinity e to the power minus st dt is equal to 1 divided by s. So in this case, instead of the s, we have s minus a, and therefore over here we will get s minus a. So we can say that the Laplace transform of the function e to the power at times u of t is equal to 1 divided by s minus a. And for this function, the ROC is equal to sigma greater than a. That means for the given function, the integration converges when the real part of the s or the value of the sigma is greater than a. So in this way, we can find the Laplace transform of the exponential functions. So similarly, we can also find the Laplace transform of the complex exponentials. So we have seen that the Laplace transform of the function e to the power minus at times u of t is equal to 1 divided by s plus a. And likewise, the Laplace transform of the function e to the power at times u of t is equal to 1 divided by s minus a. So in the exponential, if we have a minus a, then in the Laplace transform we will have a plus a. And similarly in the exponential, when we have a plus a, then in the Laplace transform we will have a minus a. So similarly, the Laplace transform of the function e to the power minus j omega t times u of t is equal to 1 divided by s plus j omega. And likewise, the Laplace transform of the function e to the power j omega t times u of t is equal to 1 divided by s minus j omega. So using the Laplace transform of these complex exponentials, we can also find the Laplace transform of the sinusoidal signals. So as you know, as per the Euler's identity, the sine of omega t can be given as e to the power j omega t minus e to the power minus j omega t divided by 2j. And here, this u of t indicates that this sinusoid exists only for the t greater than or equal to 0. So now, if we find the Laplace transform of the sine omega t, then that is equal to 0 minus to infinity sine of omega t times e to the power minus st times dt. Or instead of the sine omega t, we can put this value. that is equal to e to the power j omega t minus e to the power minus j omega t divided by 2j. So further we can write it as 1 divided by 2j integration 0 minus to infinity e to the power j omega t times e to the power minus st dt minus 0 minus to infinity e to the power minus j omega t times e to the power minus st dt. So this is nothing but the Laplace transform of the function e to the power j omega t, and likewise this is the Laplace transform of the function e to the power minus j omega t. So we have seen that the Laplace transform of the function e to the power j omega t is equal to 1 divided by s minus j omega, and similarly the Laplace transform of this e to the power minus j omega t is equal to 1 divided by s plus j omega. That means now we will have 1 divided by 2j times this 1 over s minus j omega minus 1 over s plus j omega, or that is equal to 1 divided by 2j times s plus j omega minus s plus j omega, and in the denominator we will have s square minus j omega square. That is the multiplication of these two terms, or that is equal to 1 divided by 2j times 2j omega divided by s square plus omega square, because as you know this j square is equal to minus 1. So these two terms will get cancelled out and we will have this omega divided by s square plus omega square. That means the Laplace transform of the sine omega t u of t is equal to omega divided by s square plus omega square. So similarly, we can also find the Laplace transform of the cos omega t. So once again, as per the Euler's identity, this cos omega t is equal to e to the power j omega t plus e to the power minus j omega t divided by 2. And here, this u of t indicates that this function exists only for the t greater than or equal to 0. So if you find the Laplace transform of this cos omega t u of t, then it can be given as 0 minus to infinity cos of omega t times e to the power minus st times dt. So using the Euler's identity, further we can write it as integration 0 minus to infinity e to the power j omega t plus e to the power minus j omega t divided by 2 times this e to the power minus st times dt. Or further we can write it as this 1 divided by 2 times integration 0 minus to infinity e to the power j omega t times e to the power minus st dt plus integration 0 minus to infinity times e to the power minus j omega t times e to the power minus st dt. So as you know, this term is the Laplace transform of the function e to the power j omega t, and likewise this integration is the Laplace transform of the e to the power minus j omega t. So we know that the Laplace transform of the e to the power j omega t is equal to 1 divided by s minus j omega, and likewise the Laplace transform of the e to the power minus j omega t is equal to 1 divided by s plus j omega. So now we will have this 1 divided by 2 times s plus j omega plus s minus j omega, and in the denominator we will have this s square minus j omega square. That is the multiplication of these two terms. So further we will have this 2s divided by this s square plus omega square. So this 2 will get cancelled out and we will have this s divided by s square plus omega square. So we can say that the Laplace transform of this function cos of omega t u of t is equal to s divided by this s square plus omega square. So in this way, we found the Laplace transform of the sinusoidal functions. Now we have seen that the Laplace transform of the exponential, that is e to the power minus at times u of t, is equal to 1 divided by s plus a. That means when we multiply the function with this e to the power minus at, then in the Laplace transform, this s will get replaced by the s plus a. So likewise, if we have a decaying sinusoid, that is e to the power minus at times sine of omega t times u of t, then its Laplace transform can be given as this omega divided by s plus a square plus omega square. So we know that the Laplace transform of the sine omega t u of t is equal to omega divided by s square plus omega square. But when we multiply it with the e to the power minus at, then in the Laplace transform, this s will get replaced by s plus a. So the same thing is shown over here. Likewise, the Laplace transform of this e to the power minus at times cos of omega t u of t will become s plus a divided by s plus a square plus omega square. So in this way, we can easily find the Laplace transform of these complex functions. And by following the same procedure, we can also find the Laplace transform of the sine hyperbolic and the cos hyperbolic functions. So as you know, this sine hyperbolic omega t can be given as this e to the power omega t minus e to the power minus omega t divided by 2. And like I said, here this ut indicates that this function exists only for the t greater than or equal to 0. So now, if we find the Laplace transform of the sine hyperbolic function, then it can be given as 0 minus to infinity sine hyperbolic omega t times e to the power minus st times dt. Or further using this expression, it can be written like this. That means that is equal to 1 divided by 2 times integration 0 minus to infinity e to the power omega t times e to the power minus st times dt minus integration 0 minus to infinity e to the power minus omega t times e to the power minus st times dt. So this term is the Laplace transform of the function e to the power omega t, and likewise this term indicates the Laplace transform of the function e to the power minus omega t. So we know that the Laplace transform of the e to the power at is equal to 1 divided by s minus a. So similarly, the Laplace transform of the function e to the power omega t will become s minus omega. And likewise, the Laplace transform of this e to the power minus omega t is equal to 1 divided by s plus omega. So that is equal to 1 divided by 2 times this s plus omega minus s plus omega divided by s square minus omega square. So if we further simplify it, then it will come out as omega divided by s square minus omega square. That means the Laplace transform of the sine hyperbolic omega t function is equal to omega divided by s square minus omega square. And similarly, we can also find the Laplace transform of the cos hyperbolic function. And to find that, we can use this expression, that is cos hyperbolic omega t is equal to e to the power omega t plus e to the power minus omega t divided by 2. And using this identity, we can easily find the Laplace transform of this cos hyperbolic function. So in this way, we have seen the Laplace transform of the various functions. So in the upcoming videos, using these Laplace transforms, we will do the circuit analysis. So similarly, in the next video, we will see some useful properties of the Laplace transform. But I hope in this video, you understood how we have derived the Laplace transform of some basic functions. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.